I met Jeremy through being a part-time PhD student first with Sharma and myself, and then with myself. And that's the topic he's going to present today on techno-economic modeling of circuits. And what surprised me about Jeremy, but it's part of being a more mature student, is his work rate is much higher than my full-time students. And not pointing to any particular current full-time students, but it's really interesting when someone's been in a work environment, how fast they produce stuff. They don't have time to hang around and have a cup of tea because they're doing it at night and not getting any sleep. And so I've known Jeremy through doing the PhD work, and it's been a really fascinating journey together that's involved lots of academic to and fro, supplemented by some interesting brown drinks that helped us think of things. And the other great thing I know of him, of his abilities, is that he, in this very busy period, he also sired 3 children. So him and his wife have been extremely busy. And how he managed to get, maybe it didn't worry about him not getting sleep with the 3 children, because he was up doing his PhD anyway. So that kind of put the two together. And it seems that in his part-time, when he's not doing all that, he is also the head of engineering for Weir Minerals Asia Pacific, which I assume is his hobby on the side between doing these other activities. So on that note, I'll hand over to Jeremy, who you can take on the share screen, Jeremy. It should be available to you at the bottom of the screen here. Yep.
Great, thanks very much. And can you hear me okay, Malcolm?
Yeah, take it away.
Okay, thanks very much for that introduction, Malcolm. And obviously, Malcolm's been absolutely key in this research that I'll present today, and having successfully gotten to this point. And thank you to the GCC for the opportunity to present on the topic. So as Malcolm mentioned, it's on techno-economic modeling of comminution options. So this all began, I guess, looking at with a review of existing practice. And I need to put caveats around what existing practice means here. I guess this was public domain practice for very wide-scoped techno-economic assessment of comminution. So that's what it means by existing practice. There are other practices, you know, within the halls and within EPCs and so on. But that's really what is meant by existing practice in the remainder of this presentation, what was in the, what is published. And out of that, a number of observations came, and essentially there was a lack of process response in the financial modeling, and a lack of financial response and scope in some of the technical modeling. So some of the gaps identified were, you know, ore response wasn't separated with machine and operating response. How information necessary to improve your operation wasn't necessarily available to you at a piece of equipment or unit operation level of detail. Unit costs didn't vary with many operating variables. There was a lot of P80 single size modeling throughout the circuit. And with that, you can't identify bottlenecks as clearly or capture imbalances between comminution stages and energy utilization, or power utilization, for example. There was a lack of detailed responses in blasting, like fragmentation and fine and coarse sizes. Also, blend response, for example, and competence by size, non-linearity of blending was absent. So that was some of there was also some missing modeling, like fine screening and so on. So there's a number of gaps were identified. So the aims and motivations of this research was to improve on techno-economic modeling for comminution, and really to capture the interrelationship between the blend and ore component characteristics with the machine and process parameters, and the resulting cash flow shown in that, you know, famous equation after Lane on the cash flow generated from processing some mineralized material. And its aims to illuminate and predict with sufficient accuracy the economic response in comminution with the goal of creating more value. Calibration to specific baselines did involve uncertainty, but once calibrated, insights on the direction of responses enriches insight. Also, this was always viewed with a separation between the ore and machine, and a mechanistic foundation for general application across sites. The hypotheses were that improving techno-economic modelling, combining operating and design scenarios with their cash flows can increase value, and an improved level of detail can yield results and design operating decisions different to and more accurate than the existing methods. A suite of new models were developed and integrated with JK-SimMet as their foundation, and case study methodology was employed to test these hypotheses. 2 case studies were considered, Cortez on the left and Cadia on the right. To support generalization, 3 different ore types were also used. Techno-economic analysis was repeated using new and the existing methods on the same scenario, so you can test between them. And many of the upgrade scenarios completed were carefully chosen so that we can vary six aspects listed here that we found lacking in some of the existing models and turned out to be very material to the outcome. And the impact of net present value and upgrade choice was large from these sort of 6 areas, and we'll talk more about them shortly. Just sort of a high-level picture of the technical architecture, at least the technical side of the techno-economic model is shown here. Analysis of the variables for techno-economic analysis sort of showed that they were they were large in number. So to capture this full scope, required a wide scope. But essentially, this architecture is what was employed. And in the center, you can see there's multiple JK-SimMet models, one for each sort of blend increment for where blending was considered, and a full simulation from blast designs on the left through to recovery response on the right was captured. And some of the detail around what was used, crush zone model blasting was used along with the drilling model. Jaw, cone crusher, fine screening, and HPGR models were either developed or integrated to supplement those already in JK-SimMet. And mechanistic tumbling mill models were used to identify media and liner consumption and link that to operation. Blend response in the SAG and ball mills and charge composition effects, as well as improved mill energy and various other constraints in the mills, were captured by something called the blend breakage rate function calculator, and I'll touch a little bit on that later on. Carbon and pulp model was developed for recovery, and gaps in the existing technical models like weak energy constraints or unit operation gaps were basically addressed. Detailed methods employed physics-based mechanistic models to capture these techno-economic responses where existing methods didn't. So moving on to the economic side of the modeling, this is informed by the technical side. It includes drill, blast, crushing, screening, conveying, and also primary and secondary grinding and HPGR unit cost models. These are coupled with capital cost build-ups on the basis of the scenarios and upgrades. And all of these together inform marginal cash flow calculations so we can determine value through NPV and compare that with upgrades. So some of the methods employed in wide-scope economic assessment in the literature are listed on the bottom of the screen, and that's what providing a bit more detail around what we mean by existing methods. Now, what the methodology we employed to test for improvements for the detailed methods are shown here. So essentially, first unit prices are individually verified, and then the overall techno-economic model is tested. The way we did this was that for each case study, the detailed modeling was calibrated to a measured baseline and then used to predict alternate, upgrade scenarios. This was then repeated for the same scenarios using the existing methods. And then we really compared the difference between the 2 methods to see if the difference was first material. And then secondly, we evaluated these differences to see which are significant and have we achieved improved fidelity and utility using the new tools. We'll briefly summarize the first case study, which was Cortez. It's an open cut SADC followed by carbon leach circuit. 2 main ores were processed, Horse Canyon on the left, Windband on the right. So Horse Canyon has a finer run of mine distribution, you can see here, as compared to Winban that had a coarser run-of-mine distribution. Winban is also softer in the large fractions, but harder in the finer fractions. And you can sort of see this by the A by Bs and bond work indices of the two ores. This difference in competence by size between the ores influenced the entire case study. And existing methods aren't able to adequately respond to this. So just a bit about model calibration. So first blasting to cyclone overflow is described, I guess. Image analysis was run on Winban and Horse Canyon run of mine, combined with Grizzly product and model fitted so as to capture the blast and primary crushing. An example of the results for Winban is at the top, showing good agreement. For grinding, 2 full surveys were taken, one for Winban and one for Horse Canyon, and this included, crash, stop, and grind out, with surveyed streams shown by the stars in the lower figure. Then, subsequent to that, 3 further snapshot surveys were taken of controlled blends. You can see the split there, 17, 50, and 75% Horse Canyon. These 5 surveys were mass balanced and model fitted, and that's shown here. So I'll spend a little bit more time just talking about the grinding mill architecture in a little bit more detail, and specifically how blending, charge composition, and constraint modeling was improved. So again, the approach here was using JK Simmet in the middle, multiple sheets, 1 per blend increment. We were using the very popular variable rate SAG model and perfect mixing ball mill models. The SAG variable filling after Morel was also integrated. And then this blend breakage rate function calculator was developed and incorporated to capture the blend response in the SAG and ball mill. And this is going to be described a little bit more detail in subsequent slides. And for ball milling, a residence time constraint was also integrated based on the work of Shi to provide an indication of overfilling constraint. And site-specific energy calculations were performed across the circuits to verify scenarios. And a SAG charge site-specific energy model was also developed and applied to provide insight into the expected change in performance with varying charge composition, because there is evidence that this grinding performance changes with the proportion of steel versus ore volume fraction in the charge of SAG mills. So what is this blend breakage rate function calculator that was used for blending? Basically the way in which it worked is, first of all, we had the modeling from JK Simmet variable SAG rates SAG model, discussing the SAG model first, and that was included to capture a blend response using and to become what we call the variable blend and rates model. An equivalent blend ore characterization was calculated based on individual ore components, using mass weighted averages of the inverse of the A by B from the drop weight test, and then the abrasion index and bond indices, they were functions of mass weighted averages of the components. Then for the controlled surveys I mentioned earlier, we were able to fit breakage rates across each of those individual surveys, and that's illustrated on the bottom right. You can see there in the figure, they're quite smooth with blend. And all of this was integrated into the blend breakage rate and function calculator illustrated on the top right. So essentially you input the blend proportion that you're processing, and you get a result around the effective blends, ore characterization and breakage rates. For ball mill modeling, the same approach was taken, very similar approach. The JK Simmet perfect mixing model was first used. Again, blending ore characteristics were based off mass weighted averages of the bond index. Similarly to the SAG model, 5 surveys were conducted, and you can see the fit that was conducted versus blend for those rates on the bottom figure. And again, all of those were populated back into the blend breakage rates and function calculator shown on the top right. So having calibrated the process and consumption models, an overall simulator capable of considering multiple upgrades was then pulled together. And this is it illustrated here. So this is capable of turning on and off, all 4 upgrade scenarios, and that includes the baseline. So that was just done for expediency. So on the far left, you can see multiple feeders represent different blast designs, and they were fed in from the external blast fragmentation model that I discussed previously. And these were done by components, so you could sort of capture selective blasting. You could either include or exclude full pre-crushing. Primary and secondary crushing was multi-component. And a partial mid-size pre-crush option was also included with and without pebble recycle crushing, and we'll talk a little bit about that shortly. Variable sag filling and the breakage rate and function calculator I mentioned earlier were incorporated, and a bit of a novel hybrid classification and also standard classification options were included in the ball milling circuit. So hybrid was the basically a combination of cyclones with the overflow being treated by fine screens to garner the benefits of both those pieces of equipment together and their strengths. The overall simulator was then used to model the following 4 scenarios. So the first one, the run-of-mine particle size distribution, is shown on the bottom left, and for Horse Canyon on the bottom right. So various blast designs were considered, and you can see the different fragmentations for the blast designs. In scenario 1, the strategy there was to employ full pre-crushing. So the original circuits, SABC, and this was to upgrade it to full pre-crushing. A finer wind band blast was also used, and some material was too large. And a coarser Horse Canyon blast was employed because it was already had a fine run-of-mine fragmentation. The media filling was increased in the sag to make up for the drop in ore charge that occurs with a finer feed to operate what we call as a barely autogenous grinding mill or bag. And scenario 2 employed an alternate way of pre-crushing, which is partial mid-size pre-crushing, where an even media to ore sag charge composition is targeted by crushing just the middle stream using screening, with the coarse stream being retained to act as media in the sag. It's also included as a selective high-intensity blast design, which included high velocity of detonation emulsion explosive to promote fines generation, especially for the for the competent in the fine Horse Canyon. Design 4, the 4th design upgrade option for wind band. Design 4 blast fragmentation was used, and 3 for Horse Canyon. So moving on to scenario 3 upgrade, the strategy there was to provide low capital cost scenario. It was the same blast design from scenario 1. Sag filling was increased via great design. Recycle crushing was upgraded. Finally, scenario 4 involved reducing, the strategy there was to reduce the overall amount of comminution in the circuit. To reduce overgrinding in the ball mill, hybrid classification was employed, where hydrocyclones perform the main volume of the work, followed by screens to sharpen the cut. The same high-intensity blast design in scenario 2 was again used, and sag filling was increased with great design. So here's some results from the throughput of these various simulation cases, plotted, and the detailed methods is plotted on the left. Existing methods is plotted on the right, with a comparative product sizes. So the same product size was set in both cases, and a ±5% uncertainty was applied for sensitivity analysis, and that was carried through later on into the financial results. So obviously the difference between the methods is profound. Beginning with the detailed methods, scenario 1 has a high throughput and wind band rich blends over the baseline, but the same in Horse Canyon, with no benefit being realized in full pre-crushing for this ore due to its very fine feed distribution and fine grain competence, and that's reasonable. In scenario 2, throughput is high for all blends, supported by high intensity blasting and mid-size crushing. The good sag composition provides high synergistic blending, giving a high peak at middle blends. Remember the differences in competencies by size between these ores. And that promoted a high throughput in Horse Canyon due to the autogenous grinding, the sag mill too, and fines generation, the high velocity detonation, emulsion explosive. Scenario 3 improves wind band throughput via increased blast intensity and filling, sag filling, but little change in Horse Canyon. Scenario 4 is the sag composition produces a high throughput in middle blends and overall improvement with high intensity blasting. Its performance in Horse Canyon is very good, even outperforming Scenario 2, which employed the same blast design. Why? This is due to the hybrid classification, which reduces the overgrinding of the highly competent in the fines Horse Canyon. Now the existing methods are considered on the right. Little difference is captured between these scenarios. The rank of scenarios is different to the detailed methods. They don't respond non-linearly to blend. You can see some variation with blend there, but that's a lot of the result of having the same size, product size being set as in the detailed methods. And the fines generation in Scenario 2 and 4 blasting is underpredicted. And interestingly, for Scenario 4, no significant improvement is detected due to the inability to predict fines generation in the blast and reduction in the overgrinding in the ball mill with hybrid classification. This is a couple of the surfaces of the upgrade scenario versus the blend and throughput. So you can see these together. It shows that they're dramatically different. So just a couple comments moving into the financial results now, having gone through some of the technical results. This is the overall comminution unit costs being compared. So the column graphs show the drilling at the bottom, then blasting, crushing, secondary crushing, primary grinding, and secondary grinding at the top of the column. And these are shown from the baseline on the left through to Scenario 1 to 4 upgrades, moving right. The detailed methods are at the top and the existing methods are at the bottom. And the solid green line shows the same, $350 per ton cost across both. So clearly there's a much richer response in detailed methods. And just to take a couple insights by way of example, if you compare Scenario 1 and 2, the crushing and overall costs are larger in full crushing as opposed to partial due to the increased, crushing obviously, and also the grinding costs, including the media and liner wear from bag operation. Scenario 2 and 4 have dish-shaped unit costs versus blend due to the sag charge composition and high throughputs, especially at middle blend. In the existing methods, the reverse is the case. For example, Scenario 4, shown in the red circles, it shows higher unit costs than the baseline existing methods due to their failure to capture the blast, sag charge composition, and classification improvements, whereas the detailed methods can. Another example is shown by the purple circles. So detailed methods are able to capture the high cost of full pre-crushing Horse Canyon, but the existing methods fail to. Here are the marginal net present value of the scenario against the baseline. I believe these were calculated over a 5-year period, and you can see the differences are profound between the two methods. The detailed methods are providing improved insight, and the best upgrade depends on the blend and in the mine plan. Starting on the left, the detailed methods, you can see high intensity partial pre-crushing, which is Scenario 2, was really high performing. So was Scenario 4, the hybrid classification, and it provides the best result for Horse Canyon. Negative values occur in some upgrades and blends, for example, full pre-crushing of Horse Canyon, which is reasonable. And interestingly, batch processing, so operating without blending the ore components, resulted in a significant loss of value with no other changes. The error bars are showing down the bottom plot are showing the difference in marginal net present value flowing through an assumed uncertainty on the throughput. So that's what's coming through in terms of the financial side. The existing methods grossly underestimate the value of high-intensity blasting cases. Little difference is captured between scenarios. And the response with blend is also more linear. Here, the operating cash flow per ton is shown with the assumed throughput uncertainty. Carried through. So for detailed methods on the left and existing on the right. So think of this as the value of each ton of ore milled. And it's clear that the detailed methods, the value of the ore responds with blend and scenario. 2 and 4 improve the value of the ore over the baseline for all blends. Scenario 1 improves wind band-rich blends, but not horse canyon-rich blends, which makes sense given the confidence by size difference between those ores. In existing methods, there's little response between scenarios, and it's much more linear. Despite constant price and marketing cost and grade and the same recovery model, significant differences in value of the ore is indicated, and the detailed methods illuminate these interrelationships with blend, process design, operating choice, and machine design. So Malcolm talked a little bit about the emissions side of things. So the detailed methods support comprehensive assessment of water, energy, and emissions with design and operating scenarios, as well as the economics. So some work done here, don't know if I can get rid of that, and was done for, looking at the greenhouse gas emissions performance of the various cases. And that was analysed as estimating direct and embodied tonnes of carbon dioxide equivalent emitted per tonne of ore processed for unit operations directly related to comminution. The baseline results for Cortez are illustrated on the top, and the bottom figure on the left shows the baseline versus alternate scenarios. So obviously, the lower the emissions per tonne of ore, the better. So that arrow shows improving performance heading down the page. And versus scenario, you can see scenario 4, the hybrid classification, and scenario 2 are high performing. You can also plot that comparing with the operating cash flow per tonne of ore. And I've reversed the axes here just for illustration. So improved value of ore and the improved value of the operation is going down the page. You can see dollars per tonne. And that arrow is indicating the direction of improved financial performance. And when you look at these two plots, they're very similar. So that's very interesting. It indicates that there is no fundamental, contradiction between the emissions performance and the financial performance. And some of that makes sense when you consider, a lot of the elements that are driving cost are also driving emissions, like media consumption and power consumption and everything else. So that's quite interesting to observe. So moving on to the second case study, which was Cadia. Although it's based on Cadia, there are simplifications. It's a single ore characteristic was employed across a longitudinal study of Cadia. So this study is based on Cadia, but there are some differences to true operation, but it does serve the purpose of comparing methods. So it's a gold copper underground operation, currently HPGR SABC. The study is both retrospective, so it looks back, to the original SABC operation of the mine, and then up until more recent operation, and it looks at alternate ways that paths that could have been taken in that upgrade. And then it also pivots and looks forward and says, okay, what are the potential upgrades for more recent operation into the future, and compares those, all assuming a consistent Cadia East ore is measured in 2014. And that's its parameters down there. So some of the, just in terms of model fitting, calibrations was the first step of the case study, as in Cortez. Scenario 0 was used for calibration. That was the historic SABC operation of the circuit. And that's illustrated top right. Scenario 3 was the HPGR SABC circuit of operation of around 2013. Incremental improvements were put in place up until 2016 and 2018. And scenario 3B is essentially captures those improvements and represents operation of around 2018. And that is the baseline for all marginal cash flow calculation, the baseline for all assessment, relative assessment in this case study. So some of the, just turning now to what some of the upgrades that were considered for this case study. And you can see it's really in two parts. The first is alternate upgrade pathways to get us to scenario 3B, which was the operation in 2018 and the baseline. And then, which we'll discuss next, is upgrades from 2018 onwards. So this is a longitudinal study. So the two alternate upgrades we'll talk about tonight were considered to 3B. were scenario 2, illustrated on the left. So instead of employing the HPGR tertiary and full pre-crushing, partial mid-size crushing was employed with tertiary cone crushers. Full utilization of the SAG mill was achieved with a more even ore to media composition and high filling. Scenario 2B is illustrated on the right. It's the same as 2, but it analyzed the impact of material handling choices, where the SABC is decoupled to the crush ball mill circuit, illustrated by the dashed red line there. And so the instead of the third ball mill being supplied by the third offtake from the sump, the common SAG sump, instead it is split, and it receives crushed product, ball mill free. It receives a direct crushed product appropriately fine enough to ensure operation. And a variable splitter is employed ahead of that to balance the two circuits. So the three upgrades from 3B into the future, if you like, that were studied are now described. So these are scenarios 4B, 4C, and 4D, and they're all reported by exception to the HPGR SABC circuit of scenario 3B. Scenario 4B is a mid-sized partial pre-crush employment, and it provides a bimodal feed to improve SAG composition and filling. The SAG motor was increased 10% to 22 megawatts, and bimodal feeding is achieved by modifying the double-deck screens and discharge chutes to divert a top product to the SAG mill, which is coarse, and a middling stream that's crushed, and a fine stream that's also sent to the SAG mill. As in 3B, there is coarse material bias to the third ball mill, and the operating work index was poorer than other mills. In scenario 4C, it's different again. So bimodal feed preparation for the SAG mill using double-deck screens is again employed using mid-size crushing. The circuit is also partially split between a HPGR ball mill and then an SABC circuit, again illustrated by the dashed red line. The HPGR product is fed to a series of screens, with the coarse material too large to provide a suitable ball mill feed being sent to the SAG mill. A variable splitter is provided on the screen undersize, which sends HPGR product to either the SAG or the third ball mill to balance the circuits. And the feed to the third ball mill from the SAG sump isn't implemented, removing that bias build up of coarse material to that mill. And direct feeding of the tertiary crushed product greatly improved the operating work index of the third mill. Finally, scenario 4D, while not the same, it captures something similar to the upgrade site is pursuing. My understanding is they've been able to further reduce the feed size to the SAG mill to get it operating more as a ball mill. But this is a scenario that also run. It's the same as scenario 3B, except the SAG mill is fed in a fully pre-crush with a new crusher being added. And it's operated as a bag mill, as a bag condition, and the SAG mill motor is increased to 22 megawatts. So very briefly now, I'll just touch on, so that was the detailed method for Cadia-based case study. The existing methods, I'll touch on them very briefly, but essentially the model calibration and scenario analysis was repeated with these. In this case, the Morel approach for crushing and grinding analysis from 2004 was used, using operating SMC indices, back calculated as operating indices from survey data. The same feed and product size was used from detailed methods, and simpler unit cost models were employed as well. So here are some results from the throughput, presented here again with the plus minus 5% uncertainty. Beginning with the detailed methods, these indicate that the upgrades 2 and 2B, comprising mid-size pre-crush and tertiary cone crushers, would likely outperform the 3B baseline HPGR tertiary crushing operation on throughput, and would perform similarly or better to full pre-crushing and HPGR with SAG motor upgrade of scenario 4D. This is in part due to the promotion of bimodal feed to the SAG mill achieved, and the lack of a strong HPGR product weakening effect for this particular ore in terms of ball mill bond work indices. 4C is high performing for some of the same reasons, especially given its lower power consumption. Interestingly, detailed methods don't predict 4B will outperform 4C despite the larger motor and additional crusher, and little or no gain beyond the assumed uncertainty is predicted with the detailed methods for 4D upgrade. We'll now compare the results with the existing methods. These predict lower throughputs in 2 and 2B due to inability to capture the sag charge composition effects. Existing methods over-predict the performance of 3 because it was essentially model fitted to 3B operation. The actual lower HPGR specific energy occurring at the time isn't captured. The SAG mill discharge design also resulted in lower fillings and power utilization, again, not captured by existing methods. The most profound difference occurs in scenario 4C with the improvement in SAG energy utilization and charge composition, and bimodal feed preparation isn't captured by existing methods. This is also the case in 4B. Close agreement is achieved for 4D, as this is a bag operation similar to that calibrated in 3B. So just here are the comminution costs for crushing and grinding. The majority reside in secondary, followed by primary grinding and HPGR when installed. And in detailed methods, the bag operations of 3B and 4B result in a marked increase. You don't really see that so much in the existing methods. It's much more flat with those differences because it's much more simplified and doesn't respond to the way in which the equipment is operating. But that gives you a bit of a flavour for unit costs also. Here, the marginal net present value of scenarios against the baseline are shown for the grades reported from the mine plan, which is called, the C3 grade, as it's called in this work. As in the Cortez case study, the difference in marginal net present value between detailed and existing methods is profound. So once again, both case studies illustrated this. The top figure shows the marginal net present value, including the uncertainty on the throughput carried forward. And when comparing the best 4B with the worst 4D upgrade cases, the detailed methods delineate between them at approximately the uncertainty applied, whereas existing methods fail to. When the best and worst upgrade cases according to the existing methods are compared, which are 4D and 4C respectively, they also delineate outside of uncertainty. However, the results contradict the detailed methods. The detailed methods capture effects from improved SAG composition in 2, 2B, 4B, and 4C, where existing methods fail to. And the methods only agree for bag operation of 4D. This analysis was repeated for both higher and lower than expected grades to study the influence of grade. So C1 was a very onerous low grade, C5 was a high grade. The marginal net present value versus scenario and grade surfaces are shown at the bottom figures, and you can see that the detailed methods on the left, the order of upgrade selection remains consistent with varying grade. Thus, it is argued that the grade uncertainty doesn't diminish the value of more detailed analysis of comminution. The previous NPV services are overlaid here in the top figure. It gives you a bit of an indication of how they vary to illustrate them both. Another piece was that was done was varying metal price, and that was reviewed in detailed methods across 70 to 130% of 2022 metal prices. The upgrade options that had lower unit costs like 4C were compared to higher operating costs like the full pre-crushing and bag operation of 4D in the bottom figures. Now, this is a very onerous case. It's combined with a low grade and low prices, but it's for relative comparison purposes. And what you can see is essentially the marginal net present value of the 4C upgrade is much more resilient to changing metal price, whereas 4D is greatly diminished with dropping price becoming negative. And the reason for that is 4C is a lower cost operation and upgrade option. It can also be seen that the relative differences in marginal net present value performance between scenarios widens with diminishing metal price, increasing the importance of detailed assessment. So the operating cash flow per tonne of ore is shown here for the reported grades in the mine plan, which was case C3. In the detailed methods, the value of the ore has increased over 3B baseline in scenario 2, considering throughput uncertainty, indicating it would have been a better upgrade in this regard. Scenario 4B and 4C also increased the value of ore over 3B, considering the uncertainty, indicating they would be good upgrade options. Interestingly, scenario 4D doesn't increase the value of the ore beyond the uncertainty, and existing methods underpredict the performance relative to detailed methods in all bimodal SAG feed scenarios. Scenario 4B bag operation is consistent across both methods as expected. The detailed methods produce different ore value results and upgrade rankings to existing methods while considering the uncertainty. And this analysis was repeated for a further grades, C1 the lowest, C5 the highest, per the bottom figure. And as grade decreases, the relative difference between scenarios becomes more significant. In the detailed methods, the scenarios which increase the value of the ore over the baseline mostly remain consistent with changing grade. And existing methods at low grade, none of the scenarios reported an improvement. So in conclusion, a techno-economic model of comminution and metalliferous mines has been developed and has been demonstrated using 2 extensive case studies. It's been demonstrated to better capture the interplay between ore, blend, machine, process design and operating choices and resulting financial performance. Comparisons were also made between this new detailed method and existing methods, and the resulting impact on techno-economic performance was found to be profound. The detailed methods were demonstrated to provide improved utility and fidelity and highlight opportunities to increase the mining operations value. It better captured some of the following key elements shown to have a large material impact on techno-economic outcomes. Firstly, blending effects arising from varying competence by size, feed size distributions, and non-linearity of blending of ore types. Full particle size calculation, capturing coarse and fine blast design effects, circuit bottlenecks, flow sheet choice impacts, and equipment results to particle size distributions, in for example, power utilization at different stages of grinding. Classification performance effects were better captured, including novel arrangements. Tumbling mill ore media composition and associated impacts on cost, efficiency, and productivity. Bottleneck identification and modeling true equipment and flow sheet constraints was improved, including energy, residence time, and capacities. And unit cost response with operating conditions was better captured. Various scenarios were analysed, including some novel circuit arrangements, such as partial mid-size pre-crushing, hybrid classification, and high-intensity selective blasting. These showed good techno-economic and emissions performance over some of the more common upgrade options employed. Detailed methods also support future composition by size, separate fines and coarse recovery devices and streams, novel comminution devices and flow sheets, etc. And these are major avenues to industrial improvement, and these cannot be captured with some of the existing methods. Also, it's been shown that the importance of detailed methods will increase with diminishing ore grades. And finally, it's worthy to note the wider impact on mine planning that this research points towards. In this study, the mine plan was fixed. However, with scenarios showing an improved ore value, it is envisaged that these improved insight could have a further increased impact and value when its results are iterated back into the mine planning process, as illustrated by the figure below. The interrelationships between mining and processing unit costs, time costs, and recovery were illuminated for comminution, and these new methods should be employed in financial optimization of existing plants for improved capital budgeting decisions. So that's all I had tonight. So thank you for listening, and I open the floor to any questions anyone might have.
Right. Well, thank you very much, Jeremy. You can get a sense of the breadth that Jeremy went through and the multiple points of depth that he put into it. And without having your head in there, you wouldn't know, well, where's the dramatic areas of uncertainty. So, the uncertainty Jeremy put in, we realized we don't know the uncertainty of a new, in principle, mechanistic model that's not validated. So you just say, well, let's put 5% and we'll see the effect. So it really does, if you look in more detail underneath the hood, it shows the areas that would have a significant impact on assessing value where we're currently weak. And the most obvious was media wear, which Jeremy didn't highlight, but it makes one of the biggest operating cost differences in those scenarios. And Jeremy dug and we looked for data, and it still remains an area of uncertainty, is media consumption as you change mill filling and ore type and rock to ball ratio. And there's secret formulas inside some engineering companies, but basically it's poorly understood and monitored. And it has one of the most significant effects on circuit choice. So I'm just picking out one that really became highlighted. So let's open up to any questions. You can put a hand up or just turn on your microphone and give a call. Yeah, Marcelo is bound to ask one.
Okay, so well, the rest of the team is warming up. Jeremy, fantastic work. I remember already watching part of it in the train with Malcolm, if I'm not mistaken, during one of your presentations last year. But yeah. So really congratulations. I think it's a great example on how when you use very conservative and weak existing models, you end up actually being very complacent with any change, because it swallows everything that you want to show, because it really doesn't have the details. I think Malcolm made a great insight into where I think that this is a good point that requires, of course, study to be able for us to improve the predictions. But as far as the modeling or process modeling goes, because you actually address the whole chain from blasting all the way to concentration. When you actually played around with the simulations, what is your feel for those circuits as far as the greatest, even using the detailed methods, what unit operations you believe that are most critical to improve the descriptions to be able to actually make a step up in future reruns of this type of work? Because I think it was definitely going ahead where we want to go, which is being able to put all components, not the average blends that you propose there. But I think it's important that somebody with your experience would say that, maybe, because as researchers, we try to make a case saying that, let's invest into this unit operation or that one because it's critical. But I think since you're not infatuated with anyone, I suppose, you'd be able to say that this or that would be quite important to put more time and effort on.
Yeah, so that's a great question, and a few things that stood out to me is some of that higher intensity blasting. It seemed to be low cost for a lot of value that you achieve out of that. I think another key thing is obviously the sag charge composition, I think, was a hidden thing, and Malcolm's spoken to the costs associated with that, but even just the grinding performance and the ability to generate, do productive work, that's the creation of fines with a certain amount of energy. I think that's a big opportunity. And also the classification and avoiding this. I think there's a great overlap between the two great problems we face, which is, comminution, energy efficiency, and tailings as well. And that overlap is in this creation of slimes that takes a lot of energy to do, and is counterproductive to recovery and also tailings management. I think classification technology is quite an important piece as well. It's not a very large contributor from a CapEx or OpEx point of view, But if you can sharpen the cut, you can really, improve energy. And so I think that's a few comments I would make, I think. And the other thing, just looking forward, I think, there's many unit operations and flow sheets not considered in this study. But there's a lot of emerging technology that this level of detail, when applied to those future, more novel flow sheets, I think will provide a lot of value. There's a lot of technology coming forward, and we need this level of detail and this kind of analysis in order to let us see the benefits from those. Because as you mentioned, using some of the existing methods, they kind of lock you into prior performance. So I think we're going to need a more detailed approach in order to capture that. So that'd be a few points I would make. Yeah.
Thanks. Excellent.
Thanks, Marcelo. Who else has something insightful or testing to ask? Just looking at these photographs that Jeremy's left up, a significant area where we differentiated. So Jeremy went through this in great effort, and these are based on extensive knowledge of these circuits, multiple surveys, and the shift of utilization. So understanding where the constraints are on the circuit doesn't appear in any traditional method. So it just assumes you can use all the energy, and those 2 mils sitting at the top, you're using all the energy. Not a chance. So the big thing is we shifted through blends and pre-crush and blast is changing the utilization of that SAG versus ball mill. And that's a really big hidden effect that's not seen in simple simulation. And the KDA one at the bottom, if you don't get your feed distribution correct, you can't draw the power in the SAG mill. And there's paper presented on when it was first commissioned with the HPGR, there was an issue around the circuit and you couldn't draw the power. So that optimization Jeremy spoke about took some years to implement. These, to me, is what we would be seeking in a more detailed simulation. The value there is enormous. It's 10 to 20% of value in a circuit that is not noticed. So if it all goes hunky-dory, no one notices. But if something is amiss with the blend of the ore, the rock ball composition and things, you don't pick it up with a simple power-based modeling, which is my jumping point to the fact that we're going to be introducing a new open platform through the GCC for simulation. Because you might have noticed that Jeremy used, I think it was 17 models stitched onto JK SimMet, which he ran by hand and entered the data into SimMet. Incredibly arduous to do, to test the principle. And what we're lacking is a platform with advanced models that's open so we can link other models in. And the GCC is coming your way with a proposal on that. Jeremy would have liked to have had it 3 years ago.
Yes, that would have been handy. Yeah, that's very interesting to hear that, Malcolm. Yeah, I think that's a very good point. And yeah, that you mentioned bottlenecks as well. Like some of the existing approaches, just not being able to capture some of the real constraints that exist because they don't have the level of detail at the equipment level. So you might have a bottleneck or a constraint that's not captured, and knowing that in advance from a design and capital upgrade perspective, it would be very valuable. So that's another very good point, and something that came up quite a lot during the process. So. Yeah.
Hi, Jeremy. Paul Shelley speaking. How are you? And thank you very much for the presentation. And my thoughts go to the necessity of work like this in the context that the industry is facing enormous challenges to improve productivity, to resolve the issues of the increasing complexity of the ore, of these environmental and social challenges that we're facing. I think there's an absolute necessity to do this type of work and to measure more and to try and challenge some of the paradigms that the existing modelling and the existing processes and thinking deliver for us. And you know, Malcolm's comment about, you know, what's the level of depth of understanding of grinding media and the economic sort of equation that drives grinding media thinking, you know, is consumption, you know, grams per ton and multiply it by the dollar per ton. And that is so simplistic and it's so ineffective to actually give you really, really good decisions around your choice of grinding media, your JB/JC ratio, you know, things like your discharge grate and pebble surface areas. That context that you've talked about in terms of those three dynamics of mineral characteristics, mill dynamics, and media need exploring, and it'll be driven by dollars, and it'll be driven by the emissions, and your model presented incredible insights into those. So they are my thoughts. I'm very pleased I sat in. Thank you very much on it.
Yeah, thanks very much for your comments there, Paul. And yeah, I'm pleased you got value and enjoyed the presentation. Thank you.
Right. Well, I hope the rest of you also enjoyed it. I think it's quite a monumental piece of work Jeremy embarked on. Really challenging because of the breadth and depth, and I'm pleased he could bring it forward to us. Thanks, Jeremy, and we'll catch you all at next month's seminar, I hope. We're in end of August. We might not have next one because of the SAG conference. So we'll feed back whether we move it by a week. Otherwise it clashes with the SAG conference. All right. Cheers, everyone. Thanks for attending, and thanks again, Jeremy.
All right. Thanks, everybody.
Thanks, Jeremy.
Bye-bye now.
Yeah, thanks, everyone.